Hello and thank you for listening to our presentation. I am Peter Becker. We are Team LEOnidas, consisting of me, Julian Halpern-Smith, Krikor Hachikian, Nicholas Adrian, and Riley Horling.
Our goal is to be able to effectively detect the presence or absence of artificial light sources. We want this to be accurate within 50%, and we believe that this is achievable given our hardware and our software capabilities. This goal satisfies the requirements of the challenge, and we would like to complete this by the end of the challenge season. So our satellite will take pictures at predetermined times, send those images to our ground station. Once we receive those images, we will use software to determine the exact level of light and whether or not it has increased or decreased from reference photos. Our machined chassis will provide support to the solar panels, camera, Raspberry Pi, and battery. Our Raspberry Pi will send instructions to the camera and send data to the ground station. Our camera will send photos to the Raspberry Pi and will be powered by the battery, which will be powered by the solar panel. The battery will also provide power to the Raspberry Pi.
Software architecture will be comprised of 5 states. The first one will be the central loop. This will be responsible for calling the camera and as well as be the main file running. Next will be image processor, which will take in the image gotten from the camera and strip out things such as color, and then create bounding boxes for all centers of bright pixels. Afterwards, if there's been a call for a comparison, then it will compare the just got picture and bounding boxes of bright pixels to a stored previous state, and it will take note of all differences in the level of bright pixels inside the bounding boxes. Finally, data visualization will include editing to the image itself, help of highlighting areas of change, and finally, we will go on data transmission, which will be pushing data to GitHub and then continuing the loop.
Here we have a 3D model of what our satellite will look like roughly.
So in terms of our power budget, our Raspberry Pi will require a constant 5 volts to avoid undervoltage, which with our system means roughly 3 amps for regular operations, which comes out to about 15 watts of power. This power goes to the Raspberry Pi processor, the camera, and IMU, and so on, and anything else that would be on the load for a real satellite, real CubeSat. This power can be taken in through the charger for our demo, or from the solar panel for our demo, and will be stored in the provided battery. It is a 37 watt hour battery that can charge at 22.5 watts according to the Amazon page. So this means that it would take about 1.6 hours to charge at that maximum charging speed. And if we assume 15 watts of consumption, then it would take about 2.5 hours to drain. In terms of the data budget, our images have a resolution of 3280 by 2464 pixels and are 10-bit colors, so that would equate to a 8.08 times 10 to the 7th bits file size, which for our link means that with a transmit window of about 10 minutes, we would be able to transmit 24 photos total. In terms of the mass and bill of parts, we have a number of parts listed here, most prominently our processor, SD card, and so on, as well as how much they cost. This is based on the list of parts in the courses. And then we have our mass budget based on the parts that will actually be on the system for testing, which comes out to be about just under a kilogram, or if we assume like 20% error to be safe, it would come out to be about 1,130 grams of mass that we have to expect on our satellite.
In order to test that our final CubeSat is going to be successful, we have to outline a couple goals. And those are that it needs to be able to receive power from a solar panel, and that it can take photos of desired geographical areas when instructed to. as well as being able to use the software we write to detect like various light concentrations of various geographical subjects and then analyze them correctly. And in order to test that all these things can be achieved in our goals, we have to first make sure that it's able to generate power autonomously. So we're going to do that by making sure it's unplugged from any other external power sources and then shining a light on the solar panel installed on the CubeSat to see if the power indicator on the Raspberry Pi turns on after some of the energy is generated by the solar panel. And then in order for it to work at detecting light of various geographical subjects, we're going to hold the CubeSat so that its camera is pointing towards a black piece of construction paper, which could represents a geographical area lacking light or like a place that has undergone a power outage. And then in order to like test that it's able to distinguish various light levels correctly, we're going to sprinkle various concentrations of white shredded paper that represents light in a city, for example. And then we'll see how well the CubeSat software we wrote distinguishes the various light levels and generates those results properly.
Right.
Okay, that was a great presentation. And so I had a few questions for you guys as we are exploring um, the journey of CubeSat. So my first question I would like to ask, um, I see where you talked about building a CubeSat, the design process, the hands-on experience. I see that you have gained practical skills in engineering and programming and project management, by participating in this project. So here is my first question. I'd like to uh, for you guys to answer. Can you think of any real life examples where CubeSats have been or could be used to uh, assist first responders?
I mean, I suppose like the simple reason way is that it gives you a high view of stuff. So, say if you need to like search for like I guess you say like wildfires, for instance, you can
Yes.
probably catch those from orbit and like direct people on the ground to those areas, especially in like remote places where it could potentially go unnoticed.
Okay. That is
Yeah,
okay. Go
or
ahead.
sorry, yeah, I was just, adding on to that. I mean, you can also see kind of, and not even just wildfires, but just like being able to detect light, for example, with power outages, right? I'm
Yeah.
thinking about there was an earthquake recently in Syria and Turkey, right? So you can kind of understand the actual scope. What are the big, where the epicenter is, how big is this, how many communities are being impacted by that? And then you can direct your first responders.
Okay. Good. 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 And last question: how could CubeSats be deployed quickly and efficiently to provide timely assistance to first responders?
As a satellite, I don't feel like it can be exactly like deployed on spot. It would be more along the lines of a preparative measure,
Okay.
where say a constellation of them would be able to work together, but like they would have to be pre-placed. Like I don't feel like there's a great way to like initially like deploy them on the spot.
Yeah, I would agree with that. Even with kind of the benefit of a CubeSat being fairly lower, like costs to just like put into the atmosphere, um, it would be more difficult. I mean, one thing which you can do is make sure that you've tested your CubeSat so that malfunctions don't happen, right? Because that's definitely going to be a big problem for efficiency if your CubeSats, for whatever reason, there's some sort of issue in the light sensor, etc., the cameras, whatever. So yeah.
Okay, great. All righty, guys. So as we conclude our journey through the rim of CubeSat, I hope everyone is inspired by the endless possibilities these miniature satellites offer for exploring, the Earth. So we will meet again next week, and we will dive into some more cubes, building the CubeSat challenge. Thank you.
They do.
Thank you. Bye.